Am I on? Okay. Good afternoon, everyone. Happy New Year. Hope you had a nice winter break. And this is the kickoff of the TCIPG seminar series, as you may be aware. We have these the first Friday of every month. And today's seminar is going to be given by our own Bill Sanders, who is going to present a state-based model, executable state-based model from an adversary viewpoint to quantify system security in the design, implementation, and operation of complex systems, and illustrate this with a case study in electric grid distribution systems. As far as logistics, I've been asked to request, if you have a question, use the chat feature on the webinar. And other than that, I'll turn it over to Bill.
Thank you, Al, and welcome all of you. I think we have a good crowd online as well as some people here. Our term at Illinois does not start yet, but I know the term at Dartmouth at least has started, and some of the other schools, and I know we have a lot of people from industry and I think a few people from government online as well. This is a rarity for me. Usually I get to give some big overview about TCIPG, about all the work of everyone else is doing in the project. Today, and actually it was a suggestion of one of our industry partners, I really feel honored to be able to give a more technical talk about security metrics and quantifying security. Now this is an extremely controversial topic in any circle, but particularly in the circle where really big investments are being made in the electric grid now. There is real controversy about how to judge whether that's helping. Is our electric system, or is some portion of it, more secure today than it was 5 years ago, for example? Now that question in general, although many would like to see it answered, and I think it's a very reasonable question to ask, is probably too hard to answer in the absolute or answer in a global sense. But what I want to talk about today is a way that one can look at alternate architectures that one might propose to secure a system and be able to make quantitatively based decisions about what things that are more secure than other things. I should say there are many needs for security assessment, ranging from experimental approaches, ranging from more process-based approaches to model-based approaches. And I don't want to pretend that this is the only approach and that should be used. But I think this is an important step forward in approaches for looking at alternate architectures and seeing how secure they are. So I'm going to jump through, and feel free, please, to ask questions as we go along, both the people that are online and the people that are in this room, and I hope you find this all interesting. First, I should acknowledge the work of a lot of people that this was based on. There's a whole team here at the University of Illinois, including Mike Ford and Elizabeth LeMay, who are both graduate students. Ken Keefe, who's a senior system programmer at the University of Illinois and implemented the tool I'm going to show you. Carol Murky, who's works with us on this project from the Cyber Defense Agency. And the fact, importantly, that DHS Science and Technology Office, in particular Doug Maughan, has been the sponsor of this work for 3 years now. In addition to these people that are in the core team, I should say, and you'll see this come up later, this work is a result of close collaboration with GE Research, and particularly Bruce Barnett, who motivated and helped with the construction of, let's just say, some versions of the model that I'm going to show you. And this is of course, a sanitized version, but this is a technique that we've been getting very good feedback from industry as we move forward. So what's the problem? The problem of course, is assessing how secure, how resilient a particular approach that you might want to take is. And this is a problem, as I said, that's really key in building the next generation power grid. But I think it's an approach that people are asking all around now with all of our different cyber infrastructures. I don't think I need to say much about the first point. Adversaries are out there. They're trying to affect the ability of systems to perform their missions. And I think particularly when one thinks about resilient systems, systems that even if they're partially compromised, they somehow continue to fulfill their mission, we need ways to judge how well that actually is the case. No system's perfectly secure. Some systems are more secure than others, but how much more secure are they, and which systems are the ones that we should put our trust in? And so that's what I'm going to attempt to answer, and as I said, this is by no means the last statement on this topic, but I think it's an important step forward in something that maybe 10 years ago people said would be impossible to do, and now whether everyone believes it or not, we're being forced to make these kind of decisions. So this is a scientifically based way to make those kind of decisions. So why use model-based system security and resiliency evaluation? As I said, there are many approaches. We need to use experimental approaches for our systems in the field. We need to use fuzz testing. We need to use formal methods to do proofs about implementations. We need to use process-based approaches to make sure we use good security design-based design methodologies. Why use model-based approaches as well? Well, we need to get a big picture. We can't experiment with, it's both too dangerous, and for other reasons, we can't experiment with whole systems. Systems may not even be built and may not exist. We need to understand how individual actors, individual adversaries can affect systems globally. We want to do this, why? To compare system configuration alternatives before implementing them, and to estimate how well particular systems will perform with respect to particular adversaries. So modeling of adversaries is an important part of all of this approach. Some people say, oh, we should just look at the very worst case adversary at all times. Well, I would argue there are many different classes of adversary, and we really need to understand the spectrum of different adversaries and how those different adversaries will likely attack and what effect they may have on a system in order to understand how in a more cost-effective method to secure those systems. So what's the situation today? And I admit fully that this is a simplification, but this is insight we've gained from talking to many people, both in industry and government, about how they make security decisions today. So it says typical situation today. There's really sort of, I'd say, two typical situations. One typical situation is that you rely on a wise person that you trust to make security decisions. It says a wizard here, but you rely on someone who has extensive experience in the field. Because of that extensive experience, they can make decisions about what kinds of security controls might be most appropriate, whether money should be spent on training, whether money should be spent more on hardware itself. Those may be very good decisions that are reached, but those are not decisions that can be audited. Those are not decisions that we can understand as the situation of the system changes, whether they still apply or not. And they're not decisions that, in a certain sense, that we can justify if we have to go back and understand why we made a certain decision at a certain point in time. Another approach, which we see, and we've seen this used in various industries commercially, is you rely on a committee. The argument is that security as a property is holistic and very multifaceted. There are aspects of it that involve humans. There are aspects of it that involve technology. There are trade-offs between more education and training versus more technology. And so no single person can really make the right decision. So I've actually heard it said that one company does this, is they get together a team of these stakeholders. And the team of these, and I've heard this actually many times, but in this one case, the team of stakeholders get together, they open a bottle of good wine, they take a glass, they drink it, they talk about it, and they make a decision together. That may be, again, a very good decision, but the challenge there is those people talk different languages, they have different backgrounds. Well, that might be an asset that also makes it hard because they're thinking in different currencies to make comparisons about security. So I would argue we still need those kinds of teams of people. We need those multiple insights, but we need a tool by which they can express their thoughts and can express the system, their perspectives about the system and security in a way that they can make comparisons, they can audit the result, they can go back and say, well, I think this assumption we made, right or wrong back then, now needs to be changed. And they can, over time, develop if you will, a methodology and an engineering for tracking a predictive measure of the security of the system. And that's the kind of thing we're looking at as we move forward for tomorrow. So just to give you a feeling of what's to come, this is an example of the output from the kind of analysis. I won't tell you much about what this figure is yet, but it sort of looks like an attack tree. So there's some paths that attackers might take. The yellow boxes are steps that an attacker might take to attack a certain distribution side system in the power grid. And the lines there represent outputs of an analytic analyses that tell the most likely paths that different kinds of attackers might take. And there are numbers associated with, there are probabilities that talk about likelihood of success. The absolute values of those numbers I don't believe we can depend on. But we can depend on the fact, and you'll see this as we go forward, that these are things that we need to consider. And we can use this kind of tool to tell us what likely is a target in an attack and how should we place our efforts and how to better secure a system. Okay, so that's the kind of thing, that's the kind of output, and we'd like to do this not just from informal insight, we'd like to do this based on a methodological process in which we can actually understand what the inputs are. We can agree, rightly or wrongly, that today those are the best inputs that we can base our decision on, even if they're not perfect. And we can compute results like this that allow us then to make security decisions on how to make systems more secure or more resilient. Okay, that's the goal of what we're going to try to do. Okay. So the approach that we've developed is something called ADVISE. ADVISE is motivated, of course, by much past work in model-based security evaluation. And again, remember I said model-based approach is not the only approach. We need a very multifaceted approach. In fact, in TCIPG, there's many different security analysis efforts going on, and we need that multifaceted approach. But what this approach is based on is sort of two very different perspectives we've seen in industry. One of them is an approach that focuses on a model of the system, a model of a system from the attacker's viewpoint, but that tries to capture the architecture of the system and the steps an adversary might take in order to infiltrate that system. I took out the details of these alternate approaches because I didn't think we had time today, but one of them is called attack trees. Attack trees have been around for a long time, but a very simple approach that's very similar to fault trees if you're familiar with that. But it's an approach in which you write a goal of an adversary at a root node. You write root nodes that are actions that adversaries might take, and then the tree itself expresses a Boolean relationship between combinations of those attack steps and an outcome that an adversary might take. I think it's a very reasonable approach, a very good first step, but it lacks the ability, it's a so-called combinatorial approach, and because it's combinatorial, it lacks the approach to understand, based on the state of the system, how the effectiveness of an adversary may change and how what an adversary does may change. An approach that takes the other direction and looks at a very detailed state-based approach is something called, well, both attack graphs and more specifically privilege graphs that were developed in France in the mid-1990s. And here it's a much more state-based Markov-like approach, if you're familiar with that kind of thing, where you represent the state of a system as the privilege that an attacker has achieved, perhaps in many domains, so it can be a multi-dimensional state space, but represents the escalation of privilege that an attacker has, and hence the ability an attacker has to make changes to a system, and represents then, via arcs, transitions between those privileges. But there's, in both of these cases, the model of the attacker is very implicit and typically very simple. Okay, so in a sense, you build an attack tree or you build a privilege graph with an attacker in mind, but without explicitly representing the desires and needs and the human aspects of that attacker. The other class of tools that have been used focused on the attacker and very little on the system. There's an approach called MORDA, and there's one of the commercializations of that approach is called MIR, developed by the Cyber Defense Agency that we worked with on this project. And they provide fairly detailed models of attackers' desires. Is this attacker risk adverse? Is this attacker noisy or quiet? Is this attacker likely to attack aggressively or wait, and only when he's certain that an attack will be successful do an attack? So there have been accepted ways, and in fact MORDA was developed at NSA and has been used in many analyses of this type. There are accepted ways in which to represent attackers that are somewhere in between that very gross characterization of nation state to kitty scripter, and on the other hand just looking at all the vulnerabilities in a database. But the limitation of these approaches is that they were really tailored to systems that once a first attack is successful, the game is over. It's all or nothing, right? So they model well the behavior of attackers, but they don't model the progression of an attacker through the system as is necessary for systems that we want to make resilient. Okay? So what Advise does is integrate the benefits of both these two approaches. It takes a model-based approach, it takes a state-based approach like the privilege graphs, but it does so with a very explicit and very tunable model of attackers that can help you understand for different kinds of anticipated behaviors of attackers what the outcomes might be. Okay, so that's the approach. What I'm going to do with the remaining time I have, which I think we're still doing very well, is tell you a bit about the methodology without going too much into the mathematics, and then give you a fairly detailed case study to show you the kind of results you can obtain, and then hopefully leave some time for questions. Before I do that, are there any questions or complaints or so far about what we have? Any in the room? Feel free. Any online? No? Okay, so let's go forward. So what's Advise? Advise is an adversary-driven analysis. It has a very explicit way of representing alternative adversaries. It takes a state-based approach for modeling the effect of an adversary on the system, so it considers multi-step attacks, and it looks at how the architecture of the system will influence those multiple steps. It's quantitative in its measure. It enables trade-offs between alternatives. Although it does give numbers out in an absolute sense, I would say that the absolute nature of those numbers is only as good as the inputs. And so I'm more comfortable with using it now for comparing alternatives rather than making absolute statements, right? We're not going to be able to say, you know, there's a 5/9 probability that this system will not be successfully attacked within a certain period of time. That's of course an ultimate goal and a holy grail, but I would argue that it's useful to use these kind of approaches even when we're making comparisons. And the metrics are very tunable. But typically the metrics that we use are mission-oriented metrics. They're metrics relative to the goals of the system, and can the system carry out the function it was intended to carry out, even when attackers are partially successful in their attacks. Okay, so that's the motivation. Here's just a very simple example. We'll show we'll show you a real example as we get a little farther in. But here's a idealized example of a control system and SCADA network. We may have the internet, we may have some firewalls, we may have a corporate network, and then a control network. And I'm an adversary that wants to go and infiltrate and be able to control the SCADA server, or be able to access the control network code, the code that actually is controlling the operation. Maybe on a PLC, maybe on a PMU, whatever it might be, in order to affect damage. So there then will be various attack steps. One first attack step might be to gain electronic access to the corporate network through local physical access, right? So maybe that's what the attacker would do. Maybe another option would be to gain control in the corporate network through an electronic access through the VPN, right? These are alternatives that get you perhaps to the same point, that allow you to take the next step. But different attackers may have different opinions about which step is better, and we need to understand how attackers choose among these alternate steps. Okay? So here's the advised, in a sense, in a pictorial way, the advised methodology. And what I'll do is I'll go through the various pieces of this and show you how it all fits together. You need to specify some system information. You need to specify information about the adversaries that you're interested in, and it may be multiple adversaries. You need to specify what security question are you asking, what kind of metric you want. From that, you need to generate some sort of, shall I say, executable model. Right now, we solve those models via a combination of, a variant of simulation in which an optimization is done, a game, if you will, is played at each step in the simulation to decide what the attacker will do next. We also have approaches under development that will provide close, analytic numerical solutions of these models. You solve the model, you get some metrics data, and you play what-if games with different kinds of attackers, different kinds of security controls, helping you to understand what payoffs and what decisions you should make. Okay, so that's what the goal is. So we'll start first with the system information. So we're going to represent the system information and the system from an attacker's, from the universe of possible attackers' viewpoint through something called an attack execution graph. So an attack execution graph, as it says there in a unfortunately somewhat wordy way, much like an attack graph or much like an attack tree, specifies possible sequences of behavior that attackers might take to get to goals through successful execution of particular steps of attack. Now, unlike an attack tree, which in a sense there's no state and the steps are all the steps are all independent of one another, an attack execution graph has a notion of state in which knowledge about what access an attacker happens to have at the moment, for example, whether he has internet access, knowledge about what skill that attacker has, and knowledge about what knowledge the attacker has, a system knowledge has, can influence whether attack steps are possible, how likely they'll succeed if they're tried, and so forth. So think of it as an attack graph, in a sense, but an attack graph that has an underlying, where all the decisions in the graph can be based on the state of the system, where the system represents both the system state itself and knowledge about the attacker's state, if you will. Okay, so this is just a very simple example. Here's the attack step A from the simple example and attack step B. Okay, so more formally, and again, I'm not going to be very formal in this talk. There's We can give you we have both formal papers that describe this, a PhD thesis that describes all this, and a user's manual for the tool, and we have a prototype tool that you can try if you'd like. Anyway, an attack execution graph is a 4-tuple where it's a set of attack steps, a set of access domains, or really, if you will, a state variable that tells you the position of the adversary in the system, a set of knowledge items that tells you the knowledge that the attacker has, and a set of skills that an attacker has. In the way that we've developed this, the skills are a constant for an attacker, but the attacker's knowledge and access changes over time as the attacker moves through the system. Okay, and so as an attack step is complete and is successful, you update the state of the system. Okay, and then finally there's goals. Attackers might have goals here, and attackers different attackers may place different importance on achieving different goals. Go ahead, David.
Why are knowledge and skill considered to be constant?
Right.
Past that point.
Yeah. So, David, and I'm sorry, I'll repeat the question since I didn't ask him to go to the mic. Skills are constant and knowledge is changing in the way we do this. But quite frankly, these are just words that you can represent in any way you want. You can imagine that knowledge increasing over time. In a sense, this is just a division between what we consider constant and what we consider changing. It's not like there's just one piece of knowledge and either you have it or not. Knowledge is just a class of what we call state variables, and then you can name knowledge all sorts of different things. And the important thing is that all the attack steps, as you'll see on the next slide, all the aspects of how likely an attack step can be carried out can depend in arbitrary ways on the values of those state variables. So you can represent exactly what you're talking about. So that's really important, and that's not possible in standard things like attack trees and attack graphs, which are the most widely used model-based analyses today. So that was really on our mind as we thought about how to do this. So what about an attack step? And again, I'll just go through this quickly, but I want you to give a feel for, if you will, the flexibility and the representativeness of what you can do. An attack step has a Boolean precondition. The condition just said, when can an attack this particular attack be attempted? So in this example, where you can only have this particular, try this particular attack when you have internet access and you have information about the VPN account and you have some skill in exploiting these. We should say that these variables, VPN exploit skill, account info, and internet access, these are these state variables I talked about earlier. And they can be binary things or they can have ranges of values. Again, that's up to you as you represent the system. There's some time to attempt the attack steps. The steps might take a long time, they may take a short time. Their time may affect how attackers feel about attempting them. The example there is a constant, 5 hours, but these times can be either fixed values or they can be any probability distribution function. In a sense that the limitation is the ones that are implemented in the tool, but from a theoretical point of view, this is there's the cost of attempting the attack step. There's a set of outcomes that can be the result of the attempt. In a simple sense, it might just be failure and success, but there might be different kinds of success, or there might be different kinds of failure, right? So it's a set of outcomes, and a set of outcomes, each outcome can change the state variables that I talked about. There's a probability of each of those outcomes occurring, and again, the probabilities can be fixed, or they can be dependent on the state of the system, the knowledge, skill, and access. And there's a probability of being detected when you have different kinds of outcomes, okay? So this is the way you specify the nature of a particular kind of attack step in a multi-step attack where the attacker might be trying to reach some goals. And an obvious question to ask is, well, you've got to put some numbers in here. How do you know what to put in, right? And people say, well, we don't know how to put in the right numbers, so the model must not be useful. Well, what I'd argue is we're doing it today. We're doing it in a very informal way today, right? We're thinking about those kinds of things. So whether we know the numbers exactly or not, we put in our best guesses. We think about the uncertainty in those guesses, and we do sensitivity analyses with respect to the results. This whole thing is implemented in a very mature modeling and simulation tool called Mobius, in which allows you to do experimental design and run hundreds of variants of these experiments with different parameter values fairly automatically, if you will, graphing the results and the sensitivity so you can understand how important is it how long it takes to attempt a stack? How important is it whether the attack is attempted or not with regard to your overall result? So what I'm arguing is we don't know these numbers exactly, but we do know that we can understand the sensitivity of our choices of these parameter values when we're looking for when we're looking at analyses with respect to particular metrics. Okay. And then the final one, I'm sorry, I got ahead of myself, is what's the next step that results when the outcome occurs? And this can just be any function on the access, skill, and knowledge variables that I talked about earlier. Okay? There's always something called a do-nothing attack step in every attack execution graph. And basically this is just a step that you can define it in any way you want, but the typical way is you say it's always true, the cost is nothing to do it, the detection probability is nothing, and the next state is the same as the current state. Now you can change this in the tool if you think there's some cost with sitting around waiting, which there might be. But the idea here is that you want to set up a situation, since this is a discrete event system, in which the attacker may choose not to attack at a particular point in time. And the attacker, in fact, it may be a good strategy to try to build a system in which the attacker has not, where the optimal thing for the attacker to do is not to attack. Right? So that's a portion of something you define. Okay, so that's the system information. Now let me tell you about the adversary information. Like I said, it's important to model the system. This is, if you will, an extension of approaches like attack graphs and attack trees, but state-based and much richer. Now we'd like to be able to model explicitly attackers and look at how attackers may act on that system, the attack execution graph we just developed. So again, there's a formal representation, which is actually not as complicated as an attack execution graph, and I'll go through it and give you a feel. And then again, I'll give you some more examples. But there's an initial state that an attacker has. Where does this attacker start? Is he outside in the internet? Is he on the corporate network? You can specify different starting points for attackers. In fact, that's the same kind of thing we do when we do red teaming, right? We may play different red team exercises where we suppose that the attacker has different starting points, and we look at the importance of that starting point on the overall system security. There's an attack skill level function, and that says for each attack skill that's defined in the attack execution graph, how much skill does this particular attacker have? There's an attack goal function that says how important, and we'll use dollars, but any kind of, if you will, currency, how important is it to this particular attacker to achieve this particular goal, right? And so that's, and those are listed on the goals that we had in the attack execution graph. And then this is actually really important. There's so-called attack preference weights for cost, payoff, and detection probability. Now these are not probabilities of detection, for example, but these are how important is cost, how important is the ultimate payoff, and how important is not being detected to the attacker. Different attackers may be noisy, they may be quiet, and so forth, and And different attackers, clearly knowledge we have from working again with people in government is that different kinds of attackers behave in different ways with regard to these preferences. And so that helps guide. And then this is really more a technical point, but there's so-called utility functions for cost, payoff, and detection probability. And this is just a way of, if you will, uniformizing the scale of cost, payoff, and detection. They may be in very different units in order that if you will, it's a constant weight that is applied in order that you can provide an overall solution to the optimization problem when we're determining what the attacker does. But those are usually set in fairly simple ways. I won't go into how it is. And those are usually constant through all the kind of analyses that we're doing. And then finally, there's something called the planning horizon. And the planning horizon is how far ahead does the attacker think in numbers of attack steps when planning out what is the next attack step to take. Now, if you're familiar with game theory, you're familiar with Markov decision processes, you know that a way to do solutions of them sometimes is to truncate the search space, and in a sense, that's what that is. But from a modeling point of view, it's something much more than that. It's how far ahead does this attacker think? And it aids in efficient solution of the models, but it is real in the sense that it allows us to study for different kinds of attackers that have different abilities to think ahead how effective they are. And in fact, this is something that we've been told, again, from our friends that we've talked to in government and industry, is something that probably is very real, because they tell us they observe attackers that tend to make steps that are fairly random and don't seem very knowledgeable at the beginning. But then after a while, they hone in and they make steps that are very deliberate. And typically what that is when the attacker gets close enough to the goal, the attacker can see the goal, and then the attacker can be much more deliberate. So the way in which this planning horizon is set, also together with how far away the goals are from where the attacker currently is, has a big effect on how attackers might behave, and that's important. So the important thing here in how we specify this, and I should say this is fairly similar to the way it's done in the National Security Agency's MORDA, at least inspired by that, is to represent the attacker in very concrete terms, but terms that we're comfortable in thinking about attackers. One of the criticisms of early work in quantitative security, model-based quantitative security analysis, in particular the criticisms of so-called survivability analysis that was developed quite a while ago at Carnegie Mellon, was that attackers did things that were too obvious. That you could model things probabilistically in a state base and so forth, but you had to program what the attackers did. And many people prefer, and I tend to agree, that the attacker behavior, if you will, emerges out of characteristics of the attacker, rather than requiring the programmer to program what the attacker does, right? So in a sense, attackers will end up doing things that surprise you. When we talked to one of our sponsors, they said to us once, I'd like a modeling approach in which I'm surprised by what the attacker does in your model, but then once I think about it, that makes good sense, and then I gain insight, right? So a lot of modeling is about both being surprised, but then when you think about it after a while, understanding why it happened and that making good sense, okay? So that's what we attempted to do in the way we thought a lot about how to model attackers, and that's what we attempted to do. Okay? And then finally, the model state, if you will, that during execution is just, let me go through this here, but it's the set of access domains the adversary can access, the set of knowledge items that it possesses, and what attack goals has the attacker achieved. And over time, there's an evolution and execution of these things where attack steps are attempted, state changes, and from an attacker's point of view, hopefully goals are reached, and from the defender's point of view, hopefully goals are not reached. Okay? So now what I want to do, I'll say a little bit about security question, but then I want to use most of our time to go into how do we solve these models. So in the security question, we basically can write down any kind of measures we want that tell us about likelihood that goals are reached, time it takes to reach goals, likelihood that attack steps are attempted, likelihood that attack steps are successful, and so forth. So I think you get the feeling. You see some of them here. Metrics based on state, metrics based on time, metrics based on frequency. And I think the important thing is these metrics are defined in a way that enable you to understand whether the system is able to perform the mission that it was designed to. So these are fairly high-level metrics. These aren't very low-level metrics about very particular aspects of information security. They're high-level metrics about is the system performing in the way that's required. Okay? Okay, now I'll go on to the solution. And again, I could spend a lot of time here, but I want to give you an overview and then give you, show you an example in the time we have. Okay? So, at a high level, if you think of the execution of the model as a sequence of states, then attack steps that are attempted, new states that may result, and so forth, we need to understand how that cycle occurs. So we're in some current state. We need to determine all the available attack steps in that state. So those are the attack steps whose Boolean precondition are true. We need to choose the most attractive attack step, or perhaps there's multiple that have the same attractiveness. So the set of most attractive attack steps. That's really the key part. How do we link together those adversary representations with the attack execution graph to choose the most attractive attack steps? We then, among the ones that are most attractive, one or more, we need to choose one of them. We need to update the state based on the outcomes and the state change functions, and we get to a new state. Okay, so it's a fairly simple loop, and if we didn't have this sort of, if you will, specification of an attacker that was at a high level, you might think of this as a simulation in which you're in a state, there's an event, you get to a new state, and so forth. So really the interesting part, and the part that I think is really important and evolved over time, actually with the input of a lot of people, was how do we choose the most attractive attack steps in an online fashion as the simulation is executing in order to come up with a solution. Okay, so here's a simulation loop. I won't belabor sort of the details. It's a fairly standard simulation loop. The important and interesting thing is how to choose the set of most attractive attack steps in a given state with a different given characteristic of an attacker. Okay? And what we'd like to do is a fairly, if you will, standard optimization. We take this high-level model description, we formulate it as an optimization problem. We solve the optimization problem, but we need to do it very efficiently because we're solving this millions of times during the execution of the simulation, right? After each state change. There are a lot of ways in which you can make it more efficient, but let's just think of it that way for now. And here it says, the attractiveness of an available next step is a function of the payoff in the expected states, n steps, remember n is the planning horizon from the current state, the expected, and the expected costs and detection of those n steps, okay? And to be more precise about it, the attractiveness or the function in which we want to optimize is expressed like the bottom line in the equation that's in that box, where it's a weighted sum of the expected path costs, the cost it takes to take a certain path, n steps ahead, the expected payoff when we move forward, the expected detection that will occur if we go on that path, and so forth. And in a sense, in a very naive sense, you think, well, we consider all possible paths of length n, although that can be a really large number, all possible paths, and then find out which path is most attractive, and then take the step that's the first step on that path. What we'd like to be able to do, and what's typically done in these kind of optimization problems, is to break this up in a way that we don't have to consider all possible paths independently of one another. Okay? And the way we do that is using something called the state look-ahead tree. I'm not going to take too much time in saying this, but this is a concrete example in which we are in some state. We have some number of different attack steps that we can choose between. And what that line there means that for this attack step, there are two possible outcomes. Okay, and this is with n equals 1, so it's very simple, just looking ahead. But we have to choose between, in this case, attack step 1 and the do nothing attack step. We can compute an attractiveness based on the function I said, do the same thing for the do nothing attack step. And we can see in this case, the do nothing attack step is advantageous, so that's advantageous, so that's the one that gets chosen. So when it's one step ahead, it's very simple. The set of most attractive attack steps is just the do nothing attack step. It gets a little more tricky in which you want to look n steps ahead. So you remember that's the equation. We go through the computation. In a sense, what you do is you recurse down the tree, computing attractiveness of, at the lowest level, in a sense, we've computed the attractiveness of these two attack steps. Among these two, we choose among these two, this is the most attractive one. We then do the same for the other possible outcome of attack step 1, and we say that in that case, if it's the second outcome, the do nothing one is the most attractive. We then compute an overall attractiveness based on the weighted probability of the outcomes of those two different outcomes of that attack step. We go down and do that for the other option in this case. And in this case, we see that, I'm not very good with animation, we see that attack step 1 is the attack step with the greatest. In a sense, for those of you who know Markov decision processes, this is just a typical solution of a Markov decision process, but it makes a certain assumption, and I'll go into this. This is just the equation, we won't worry about this. It makes an assumption that basically that we have this Mellman's principle, which says that we can make those choices, if you will, we can prune by computing attractiveness at each level as we work our way up. We can prove, and Elizabeth in her thesis did prove, that this is an optimal policy with regard to the attacker intent when it's wholly linear, which means that we have non-zero weights on cost and payoff only, or when it's wholly multiplicative, where we have non-zero weights only on detection. Unfortunately, in a sense, it's not always optimal. It doesn't provide, if you will, worst case behavior for attackers when we combine detection with either cost and payoff. Okay? So in a sense, this is a natural way to do it. It provides behavior that seems reasonable with regard to attackers, but it doesn't have this worst case nature we'd have, because within the parameters of how we specify an attacker, we'd like to do an analysis that shows what the worst case behavior of the attacker is. Now, I want to leave time for the example, so I'm not going to really say too much about this, but we can play a trick, and if we look at the log of the non-detection probability rather than the detection probability, then we get something that's additive, and then we can come up with an optimization function that is always optimal. And so more of that can be said, and I can say more about that later. Okay, so what's the practical implication is, as I said, adversaries using this algorithm will exhibit the worst case behavior that's, in a sense, execute an attack step that's best for them, considering their attack preferences, their planning horizon, their attack steps, and their attractiveness function. So here we can study different kinds of, we can learn from the model different kinds of behaviors different kinds of attackers would take. Okay, I have a few minutes and I want to show you a case study. This case study is a study of an electric power distribution system. It analyzes the security impact of adding, in this case we analyze security impact of adding radio communications between substations and pole top reclosers. There can be advantages to this because we can use that communication to recover from failures that have occurred, just thus aiding the delivery, continuous delivery of power. But there can also be disadvantages because perhaps the radios can open up security holes that can be exploited by an attacker. So we need to understand an architecture of a system and how a feature that's added, in this case a feature that's added to aid with the continuous delivery of power, to aid with the availability of the system, what the security implications of are, the addition of that. This is a generic system. You can find this kind of architecture in many books. For example, the book by Ed Schweitzer, which is a great book on architectures for power systems. You can see this in the commercial products of several vendors. And again, I don't have a lot of time, but you can see that the model that's built involves this, the communication path from the SCADA control center through its communication network, through subsystems, all the way down to the pole tops that are controlling the final distribution of power, say within neighborhoods. Okay? Here's a attack execution graph example, a real example based on that. I can't label all the different kinds of access, skill, and knowledge that are here, but you can see the attack steps. If you're interested in this, we can actually provide you with a detailed description of the model, or if you're really interested, an executable version of the model that you can play with yourself. And there are various goals that the attacker has, and you can see what they are. Sabotage a single recloser, sabotage multiple reclosers, damage the equipment and cause a disruption, install a backdoor software on the reclosers, various things the attackers may aim to do. Okay? This is just the mapping of the physical system to the attack execution graph. This is a description of the different attackers we wanted to consider. And we considered here 6 different attackers, you can see, from a foreign government to an insider technician, that's out in the field, to an insider technician that happens to be in the control system network itself, to an inside engineer. There was an engineering portion of the architecture as well. And I won't really take the time to argue about why the weights are the way they are. And as I said, I don't imagine that these weights are exact, but they're very clear, I think, if you thought about them and you read what's down below here, you'd see that it makes sense that, for example, a foreign government may have little concern for cost, may have roughly equal preference for not being detected and obtaining the ultimate payoff. And different folks there may have different weightings. So, for example, a hacker might care quite a bit about cost and so forth. Yeah, so we can study the effects of these different kind of attackers. Is that a question? Yeah, can you pull up? Good question. So that was, yeah, the question was, how is the prevention or the defense step that might be taken for an attack accounted for in the model? The answer is, in everything I showed you in the talk today, it isn't. So that's good you were listening carefully. The reality is that this attack execution graph model in the Mobius software, with which Frederick Sheldon, who asked the question, is familiar with, that this attack execution graph model can be composed with a model of the defender's action. And that defender action can also change those state variables of the model. So in fact, in this model, I'm keeping it simple for the amount of time we have, we've built examples where we show how different kinds of defensive actions can be used to change the state of the system back away from those state goals. So in a sense, I didn't show it, but you use a different model, for example, a stochastic activity network model, with shared state variables on this model in order to model the either the response of the system itself or the response of a human defender that might be defending the system. But that's a great question. Tell you're awake. Here are the kinds of things we want to learn. What's the average number of attempts of different attack steps? That's pretty important if I'm a defender, right? We've been doing this in red teaming exercises because I want to understand which attack step attackers are going to likely defend, and that will tell me which parts of the system I need to harden the most, if you will, right? The probability that different goals are achieved. I want to know, do I have to be more worried about one goal or another goal with regard to attacker? And the average time to achieve the goals. How long, given that I do achieve the goals, does it take before I achieve the goals? And again, I don't have a lot of faith in what we're doing in the field now, the real work we're doing with this tool, in the absolute values of these numbers. But I have quite a bit of confidence from all the sensitivity analyses we've done in understanding the relative natures of these, and the relative natures are what I use to make these decisions with regard to the system. Here's a real example, if you will, a screenshot of the implementation of this attack execution graph in software. Here's an example of the implementation of the adversary model. I see questions are flowing in. Let me just quickly finish and then I'll answer questions. So here we can see this particular attacker has certain skills, has particular initial access, initial knowledge, and has particular goals with certain payoffs on the goals. And then the outcome comes out is measures that tell me different paths attackers to take, the likelihoods of those paths, and so forth. And I just represent this pictorially for you, where I show you that for all the different kind of adversaries we consider, the different kinds of paths they've taken. And I think even more interesting is this is without the recloser radios that I talked about, the feature that could be added that may aid in availability, but may provide opportunities for attackers. And we can see when we add the recloser radios, look at how the attack behavior of the attackers change, right? In fact, they tend to focus their behavior on sending command to the reclosers in order to try to thwart them. And so that tells you a lot about how you have to defend the system. The only one that doesn't do that is the insiders, right? The technicians and the operators. They've got a different path in order to achieve the goals. Okay. I think in interest of time, I won't say much about this, but these are the speeds of different kinds of attacks, different kinds of attackers, the most likely goal that they will try to achieve, and how long it takes them to achieve the goals. So it's interesting to look at this and see different attackers have different kinds of goals, also how long it takes them to achieve those goals. To look at different attack steps. This is an incomplete graph in a sense. This is an attack step, and it tells you how often it was attacked. And so what you really have to do is look at this with a table that also tells you which attack steps different kinds of attackers use. Again, that's interesting to understand the behavior. And that's really what I wanted to show you today. Again, I'd like to acknowledge all the Mobius team. I'd also really like to acknowledge our collaborators at GE Research. I think Bruce might be online. That was a really big help, and they've been our partners in using this tool, providing feedback, as well as another 10 organizations or so that have done an alpha test of this tool and used it on some of their own security problems. So to summarize, and I think then maybe I have 5 minutes left for questions. This isn't, as I said at the beginning, this isn't the end of the story on quantitative security evaluation. I think it's the beginning, and a very credible beginning, of learning how to change security, if you will, the security craft, as many people call it today, into a real security engineering where we can make design decisions about where to place our efforts with regard when we develop a security architecture for a system. There are many other things we need to do. We need to study the process of development. We need to red team. We need to fuzz. We need to do careful analysis on the implementations once it's built. But if the architecture isn't the right architecture, there'll be flaws whether or not I introduce more flaws in the development of the system. Mobius SE, Mobius Security Edition, with the advised modeling approach that I told you here, I think is a very credible way to do that. We'd be happy to work with anyone in industry or academics who wants to try it. And there's work going on now on analytic solution methods for these models, and also on very explicitly modeling the behavior of the users, the good humans, as I like to say, as well as the attackers. Because you can imagine that the users, the good humans, can impact the security of the system just as much as the attackers, right? By engaging in risky behaviors, right? If the password policy is too crazy, they'll write the password down on a piece of paper because they won't be able to understand it. So we need to understand how security technology and security policy impacts human behavior, and how that human behavior impacts the creation of vulnerabilities in the system that a attacker can exploit. So just like in response to the question that says, how do you model the defense response of the system? And I answered, you model it with a separate model that I composed together with the attack execution graph. We're working on an approach where we compose together a model of the human user of the system and how that human's use can introduce or avoid vulnerabilities that then the attacker model either exploits or not. And I think we need that whole picture, that holistic picture, to really understand in a predictive way system security. So I probably only have a few minutes. Why don't you start with a few questions and then online first?
Okay, so the question was, is this framework, including the attack graph generation and risk assessment, is it scalable to large-scale networks?
Good question. The limitation in the scalability is really in the solution of that optimization equation at each step. And the answer is, I don't have any theoretical answer to this right now, but from a practical point of view, those models I showed you there, which are very realistically sized models, take a few minutes to compute, right? I forget, Michael, 5 minutes, something like that, to come up with a full solution. So it's on the order of minutes for realistically sized systems. I can surely build a model that will overwhelm and blow up, but generally speaking, we think it's fast enough to be used for practical models. So another question?
One other question.
Come up to them. Oh, there's only one mic. Okay. There's another mic. Okay, ask one more and then we'll ask one here.
Okay. Is it necessary to understand the math in order to use advise?
No. Definitely it's not necessary to understand all the math. On the other hand, you should understand something about the assumptions that are being made in the modeling approach. I mean, a fool with a tool is still a fool, as a lot of people say, but clearly you don't have to understand Markov decision theory or any kind of optimization theory. But you just need to be able to build graphical models using the approaches I showed you, using the editors, and you should understand a bit about what's going on under the covers. And that's true of any approach you might take. I mean, I think it's important you understand what you're using. Question there?
Just my question is like for the security metric that you mentioned, like
Yep.
the number of the attempt or the probability of successful attack. So does this metric applies to the whole system, or you can apply to the different components?
You can apply them either to the overall system or to individual components. I mean, more interesting usually is the overall system. Think of it this way, and I can't remember if you've used Mobi or not, but it's any kind of metric that you can write as a function of any kinds of knowledge, skill, or access, or whether goals have been reached. So basically, whether a goal is reached is a global thing. And but yeah, it's very flexible. It's hard.
I ask this question because I want to know that whether from the result of this model, is it possible that you know where to patch for the system?
Exactly. So that's why, to go back a bit, this shows you different kinds of attack steps, and an attack step is probably a local thing on a particular component or an attack on a piece of software or so forth. Now, this isn't down at the level of looking at source code and say, there's the flaw in the source code, I should go patch it. But it tells me that particular function, that particular local function, that piece of code that implements that function is shall we say, high real estate target for the attacker. And so I better use all good software engineering techniques for security I can on that piece, because that's the one I should be most concerned about, and maybe I'm not really concerned about something over here. See, so it's at that level. It's not down in the implementation level, it's at the architecture level, but it's at the component level. Question from Al?
Okay, yeah, sorry to keep extending the time, and this may have a yes or no answer, or you may want to give a more explanatory answer. And this is, do you have the ability to express state at different levels of abstraction? And then if so, if you get an answer, does the model somehow identify I should expand the abstraction of this state so that I get a better picture of what's going on?
Yeah, it's a good question. I think everyone heard it since he used the mic, so I'll just answer. It's totally up to you at what level of abstraction you write the state variables, the knowledge, skill, and access, right? Access could be, I have access to this machine room, or it could be I have access to this piece of information in this database, and so forth. So it could be at many different levels of abstraction. Same thing for attack steps. You can represent them at a high level or not. So it's totally up to you at what level of detail you represent state and at what level you represent the attack steps. Now, does this help to guide you? This is really a modeling question. So I represent something at one level of detail, and I see, wow, that's a pretty important part here, right? So that will suggest to me that I can go from a human point of view, not automatically, I can go and I should add more detail here and try to figure out what parts of that are the attractive part to go after. But that's up to you as a modeler to do. There's nothing automatic to do that. But definitely, when you're a security analyst and you're doing these kind of investigations, that's exactly what you ought to be doing. You focus in. You focus in either by doing more modeling, or you focus in by saying, well, I know it's there. Let me now go use some other approach. Let me use a fuzzing attack approach on this component to tell me what are the parts I should be concerned about, right? So again, it's a holistic approach. We should use different approaches together, but it's a really good question. Well, they're telling me I have to wrap up, so I want to thank you all, and thank you in particular for letting me give a technical talk like this, and we'll see you next month. Next month will be the first Friday of the month, and it will be Jeff Daigle from P&L that will be coming and making a presentation.
So let's thank the speaker. Set a high standard for the seminars for the year.